Hi everyone, and welcome back to another episode of Dr. Kyle Explains, your YouTube channel where we go through GCSE science content quickly and easily. Now today we're going to be going through the properties of ionic compounds, essentially ionic bonding part 2. And so if you haven't yet seen my first video on ionic bonding, please do go through my video playlists, find the video and watch that first, as it has some really key information for the rest of this video. Thank you for everyone who is liking the video and subscribing. It really helps the channel out. So if you haven't yet, smash that like button. Please do subscribe to the channel, grab a pen and paper, and let's go ahead and jump in. Okay, so just a really quick recap on ionic bonding. So an ionic bond is between a metal and a non-metal. So just to remind you, you can have a metal such as say potassium, you can have a non-metal such as say fluorine. There's your metal, there's your non-metal, so therefore it's an ionic compound. Now this is in contrast to say something like carbon dioxide, non-metal, and so therefore that's something called covalent, but we will go through that in another video. So just remember, whenever you see a metal and a non-metal, it's an ionic compound. Now metals lose electrons to become positive, non-metals gain electrons to become negative, and then there is something called an electrostatic force of attraction between these ions, the positive metal and the negative non-metal, and they essentially come together and form the ionic bond. Okay, so some key information for today. So an ionic compound forms something called a giant lattice structure, and this is really important key language for your GCSE. Ionic compounds are held together by strong electrostatic forces of attraction, and you need to remember that they are strong, between the oppositely charged ions. These forces are acting in all directions, and so the ionic compounds tend to have very high melting points, and they can conduct electricity when molten or dissolved. Okay, so let's look at the structure in a little bit more detail then. So we just called them a giant lattice structure, and I've shown you some diagrams just below here of what these giant lattice structures look like. Now you specifically need to be able to look at these structures and recognize them for sodium chloride. So I've shown you the diagrams here for sodium chloride. However, you do not need to learn how to draw these, you will simply just have to recognize it as a picture in an exam. So whenever you see these kind of structures, that means they're ionic compounds. Remember, the other giveaway is the fact that we have a metal and a non-metal in this diagram. So this one's known as a ball and stick diagram. And we also have our positive ions and our negative ions, which is again another giveaway that it is an ionic compound. Over on this side, we have what's known as a space-saving diagram. And again, the giveaway here is that we have the negative and the positive ions in the structure, showing that it's an ionic compound. So just to reiterate, you do not have to learn them, you'll never have to draw them, but you would have to recognize what they look like in an exam. So whenever you see a structure looking like either this or this, it means it's an ionic compound. Okay, so I just want to quickly recap what an empirical formula is. So an empirical formula is a formula of a compound in its simplest form, and these are used all the time for ionic compounds. So to give you an example, I've used glucose. Now this isn't an ionic compound, it's actually covalent, but it's still good for the example. So the formula of glucose is C6H12O6. And so if we wanted to represent that in its simplest form, hopefully we can see there is twice the amount of hydrogen compared to our carbon and our oxygen. And so therefore we write the formula as CH2O. So what this formula tells us is that for every carbon, there is twice the amount of hydrogen and the same amount of oxygen. Now, how you would work this out is you would just simply divide 12 by 6 to then get your ratios. So we can deduce the formula of sodium chloride, that it is NaCl, by looking at the structure below and of the space-saving diagram. So looking at these two structures, say below, it's more onto the side here, but looking at these two structures here, we can tell that the formula must be NaCl, because for every sodium you have one chlorine. For every sodium, you have one chlorine. For every sodium, you have one chlorine. For every sodium, you have one chlorine. And it keeps going throughout the structure like this in a giant lattice structure. So when we say sodium chloride, it doesn't mean one sodium and one chlorine. It means a ratio of every one sodium, there must be one chlorine next to it in a giant lattice structure. Okay, so some common questions then that often come up for ionic bonding. So why does magnesium chloride have a high melting point? If you want to have a go at this first of all, please do feel free. Pause the video. I'm just about to go through how to answer this question. So the first thing you want to do is you want to identify that we have a metal, so magnesium, and we have a non-metal, chlorine. And so straight away, you need to identify that it is an ionic bond. If you notice, it doesn't tell you that in the question. The next thing you need to identify is that it says high melting point. And so if something has a high melting point, you should straight away think it has a strong bond. It has to. You can't have a weak bond for a high melting point. That doesn't work. Okay, so let's go into the answer then. So magnesium chloride has a giant lattice structure. So whenever we identify something as ionic, it has to have a giant lattice structure. It has strong electrostatic forces of attraction. And remember, we've seen that it's got a high melting point, so therefore it must have a strong bond. And remember, all ionic bonds have electrostatic forces of attraction between their ions. So we know it's an ionic bond, it must have electrostatic forces of attraction, it's got a high melting point, it must have strong bonds, and because we've already said it's ionic, it has to be a giant lattice structure. So these forces are acting in all directions, and so the last point we would then write is that we need lots of energy to break these bonds. So whenever you have a question asking about either a high or a low melting point, you always finish it at the end by either saying it requires lots of energy to break those forces in regards to a high melting point, or if it's at a low melting point, you would say, so not much energy needed to break those forces. So always use this layout when answering these kind of questions. So just to recap, first of all, identify it's ionic. Then see that it says high, so the bonds must be strong. Then we go ionic, must have a giant lattice structure, must have strong bonds. We call those electrostatic forces of attraction. They're acting in all directions, and so therefore lots of energy needed to break those bonds. And if you follow this structure, you'll get really good marks in your GCSE. Okay, so another common question then is explain how NaCl can conduct electricity. So again, if you want to have a go at this first, please pause the video. If not, just carry on and listen to this part. So NaCl then, ionic compound, metal, non-metal, so therefore we know it's ionic straight away. So if we remember earlier, it said that ionic compounds conduct electricity when molten or dissolved. And so our first line is that NaCl can conduct electricity when molten or dissolved. So that means we're either going to melt it or we're going to dissolve it in water. So we've got our structure over on this side here of our NaCl. And so once you dissolve or melt these ions, the ions are then free to move, so they can carry the charge. So your 3 marks are coming from they can conduct when they're molten or dissolved, ions are free to move, and so they can carry the charge. So if you look at this diagram here, what essentially is happening is when you either melt it or dissolve it, you're breaking apart this giant lattice structure. And so when it then enters into the solution, all these ions can now move around freely in all different directions, and if you essentially connect it up to kind of a circuit, the ions can carry that charge throughout that solution. Okay, so I thought I'd finally finish off with just giving you another question for you to have a go at. So can you explain why calcium oxide has a high melting point? Pause the video and we'll go through the answer. Okay, so I thought I'd write this down with you as we go. So first of all, we're going to look calcium, oxygen, oxide. So we've got a metal, non-metal, therefore it must be ionic. Then we're also going to look, it says high melting point. So we're going to plan this and we're going to think, right, strong bonds. And then it's asking about melting point. So we need to say energy at the end, some kind of comment. Okay, so my first thought then, I know it's an ionic compound. I'm going to say calcium oxide has a giant lattice structure. Remember, all ionic compounds have a giant lattice structure. Right, what else do we know? So, again, another trigger here is the fact that we've said giant, but we've also said high here. If something is giant, if something is high, it must have strong bonds. So we say, so it has strong forces of attraction. What do we call those forces of attraction in an ionic compound? They're electrostatic forces of attraction between the ions. These forces act in all directions. And so finally, it's asking about a melting point. It says it's a high melting point. So we say, so lots of energy is needed to break the forces. So you're going to need lots of energy to break those forces and to melt that compound. So again, just to show you where your mark's coming from, giant lattice structure, the fact that we're saying strong bonds and electrostatic force of attraction between the ions. This sentence here doesn't tend to be used so much in the mark scheme, but I always think it's important to say. And then we just say right at the end, whenever it talks about high melting point, so lots of energy needed to break those forces. Really well done if you've got marks there. Okay, so what we've done today then is we've described and explained the properties of ionic compounds, including their melting points and boiling points and when they can conduct electricity. And we've worked out the empirical formula for ionic compounds. Thank you so much for watching. Please do keep supporting the channel by liking the videos and subscribing. If you want to find out any more information about your GCSE science, please do go through my playlists for more GCSE content. Remember, if you ever need help with the GCSE, Dr. Kyle explains. Thanks very much. Bye-bye.